and pencil in hand, pen, to make some jottings, so keep abreast of what's to be done. You don't want to just sit there and listen, entertaining though it is. You actually need to be doing stuff to develop an understanding, to try things out before you sort of have a break over the weekend and forget what was going on. So it's important that you actively participate and do things. So thank you, Dr. French.
Hey, thank you, Robin. And I hope you're all safe and cozy as Storm Eunice hits. I'd like to think after the weather talk last week, I've now got the gift of prophecy at GCSE in clairvoyance I did on the Isle of Wight many years ago, served me in good stead. Anyway, joking apart, keep safe. So we're going from weather, terrestrial phenomena to things which are beyond the Earth. So as the title suggests, tonight we're going to have a look at gravity. We're going to look at Kepler's third law of orbital motion. And we're going to look at exoplanets, one of the hot topics of the last few years. So these aren't just planets in our solar system. These are planets in other solar systems. And we're starting to be able to detect these things directly now. So a few years ago, I think there were about 700 exoplanets detected. There's probably into the thousands now. And with various new sky surveys, this will, many, many more. Pretty much every solar system, every star will probably have planets. And maybe some of those will in the Goldilocks zone, which might support life. And of course, that's the grandest aim. So there's going to be a kind of a tour of kind of the maths and the physics and the computational work that goes around this kind of problem. And what we'll do is we'll sort of dip into various bits of Excel, bits of computer programming as is. So it's not going to be a kind of an Excel exercise like some of the earlier sessions. However, if you've downloaded the zip file, I would encourage you to open up some of the Excel files, and I can point you how to have a good play with them later. So let's have a look at this. So extrasolar planets and Kepler's third law. So this is Kepler's third law. The square of the orbital period is proportional to what is essentially the orbital radius. It's actually the semi-major axis of an ellipse. And the bit in front is a 4 pi squared, a constant. This relates to Newton's law of general gravitation, the gravitational constant, and these are the masses of the star and the planet. So looking at binary systems here, things get rather more interesting when you have more than one object that has sort of comparable mass. Anyway, so this law seems to not only work extraordinarily well for our solar system, but works extremely well for lots of other things beyond our solar system. So this is one of the major graphs which we'll get to. So what I'm doing here is plotting literally Kepler 3, the blue, against the data in the red. And you're seeing that these overlay very, very nicely. So the ones which are off that kind of curve, that's t equals a to the 1.5, if you see what I mean, well, because the masses are different. All right, so not every star has the same mass. In fact, there's quite a large variation in the masses of the stars, so big M in this case. But anyway, although we've got some very, very large uncertainties for some of these measurements, the model works extremely well. So that was for 648 exoplanets. And this is an image by an artist called Martin Vargic, which sort of is an artist's impression of what some of these planets might look like. So that one looks a bit like Uranus. That looks kind of a Jupiter kind of thing. Who knows? There may be some Earth-like planets in there somewhere too. Right. So let's do some basics. Some of you may have studied this already. Some of this may be new to you. So let's go from scratch. Right. So firstly, some history. So this is Nicolaus Copernicus, and prior to this, we're talking about, the Earth is the center of the universe. And trouble is, this is a bit of a problem. You can have the Earth being the center of your coordinate system. There's absolutely nothing wrong with that. But expect the motion of the planets, particularly Mars, to be quite complicated. All right, the sun goes around the Earth, and everything goes in strange cycles. Well, people like Copernicus will think, well, hang on a minute, why don't we have the sun being the center of the universe? Wouldn't that simplify things enormously? Of course, that got him into a huge amount of trouble with the sort of religious institutions at the time. But thankfully, the appliance of science and facts, well, whatever your beliefs, this is the truth. And in fact, the universe is a much, much grander, on a much, much grander scale than any of people in those times would have ever imagined. Which, whether you're religious or not, is a very beautiful thought. So Tycho Brahe was possibly the world's, or certainly Europe's greatest astronomer at the time, 1546 to 1601. Interestingly, he lost his nose in a duel over the legitimacy of a mathematical formula. So in the 1600s, 16th century, maths was a dangerous business. Anyway, Johannes Kepler was sort of a contemporary of his, and he was able to access Tycho Brahe's excellent data. And this is before Newton's laws, this is before calculus. Kepler was able to analyze this data. And interestingly, the orbits seem to match his rough here, whether that ellipse matches the dynamics that he was discovering. But he came up with three laws of orbital motion, looking at the planets going around the sun, a heliocentric model taken from Copernicus. And although a lot of these orbits, particularly the Earth, is very circular with the sun at the center, that's not quite true. And Mars, as you can see from this picture here, this is a fairly accurate model of the solar system. So Mars is closer to Earth at certain times of the year, and at other times of the orbits, it's further away. So the Martian orbit is quite elliptical, a squished circle, if you like. So what are these laws? So I hope this is big enough to see. I'll read it out anyway. So number one, Kepler 1, the orbit of every planet in the solar system, read that any binary star system or star and planet system, the orbit is an ellipse with the sun at one of the two foci. So an ellipse is a squished circle, and these are the foci of the ellipse. All right, if it's a circle, the focus is the center. So a line joining the planet and the sun sweeps out equal areas during equal intervals of time. Now, I think this is fascinating. I would love to know how Kepler figured this out, because that's one of the things which, when you study the dynamics of this, in fact, this is a differential equation, the rate of change of the area swept, which is A, turns out to go as the square root of the semi-major axis. So all these things are constants. So this is a constant, and it relates to angular momentum and lots of other things. But if you don't know any of that, how would you work that out? So I think this is really a fascinating story. So this, as far as we know, comes from the data. And Kepler 3 is the one that we're going to be focusing on a lot of today, which is the square of the orbital period. Sometimes I'll call it T, sometimes I call it P. Sorry about that. If you're doing rotational dynamics, having a period being in T is unhelpful because T often means tension. So confusion can result. So P means period in this particular case. Unless you have power and then you're really stuffed, you have to invent another symbol. So the square of the orbital period, how long it takes to go all the way around, all right, is proportional to the cube of the semi-major axis, which in this case is 2a would be this long axis here. All right, it's a circular orbit, that's the orbital radius. So I'm not going to prove those today. That's something you'll do when you apply Newton's laws, but we're just going to sort of appreciate where they come from. This is an interesting concept. This is the eccentricity of an ellipse. So I think we'll define those quantities, I think, on the next slide, and the polar equation too. So here we go. Here's an ellipse. Here's a much more elliptical orbit, something like Pluto. It's not really a planet, a dwarf planet. So it's going around the sun. It's going faster and closer at this point and further away at this point. These little blue stars are the foci of the ellipse. And so what you can do is you can define an ellipse or the orbit in what we call a polar coordinate system. So rather than X and Y, the sort of symmetry of this lends itself to using angles. So that's theta and radians from the horizontal, and radius. And what you'll see, of course, is that the radius varies. Is this 1 over 1 plus a bit of cos theta. If my eccentricity is 0, in other words, B is A, so that means it's a circle, then R is A. But as our little epsilon, our eccentricity, gets closer and closer to 1, then we obviously, that becomes bigger and bigger, that becomes a bigger change. All right, and so we can get more and more elliptical in our orbits. So a couple of bits and bobs. So you can prove all these things. The full analysis can be a little bit epic for full elliptical orbits. I can show you where, if you're super keen on this, you want to have a good go. So this is my website, the Eclecticon. This is the BFO page. And if you go onto physics, onto notes and cosmology, you'll find Kepler's laws and universal gravitation. There's also a derivation of Kepler's laws here. So I don't know if I've got a little, I can load that up. So let's have a look. So here's kind of one of them. It's not too difficult, actually. It's really a bit more to see. But if you want to get some notes to work through this yourself, that's not a bad place to start. Right, let's go back here. So we've got this Kepler 3. So we've got a model. We can these are plotted in MATLAB. I'll show you some of those soon. But the first thing we might want to do is see, well, does Kepler 3 work for our solar system? So let's get some solar system data. So these are the planets. I've included Pluto. Again, that's not a real planet anymore. It's been demoted. Although the recent probe that actually went to Pluto, New Horizons, has shown Pluto to an amazing place. So I do recommend having a look at that. You know, those images were extraordinary. So this is the distance from the sun in astronomical units. What's an astronomical unit? Well, that's the average distance from the Earth to the sun. And the Earth's orbital eccentricity is quite close to 0. So we can take the Earth as a circular orbit. So this is all relative in Earth masses. So Jupiter's a whopping 318 times the mass of the Earth. Saturn's not too far behind, and it's quite a lot far behind actually, 95.16. Neptune's 17 Earths, and the Sun is 332, well, call it 333,000 Earths. All right, so basically the mass of the Sun dominates the solar system. So essentially, although we'd have to take into account the other planets, for very, very precise calculations, when we're looking at solar system modeling, the planet and the Sun, we could treat it as a binary system, 2 objects. Early in the solar system, according to the recent Brian Cox documentary, the Sun, Jupiter went on the rampage early in its life. So in that case, the action of Jupiter would have been quite important for early Earth and other planets. Possibly, it's theorized the formation of the Moon came about because a direct collision with the Earth, a sort of proto moon, and the Moon sort of was formed from the debris, and that might have been caused by Jupiter getting much closer to the Sun at that point of its life cycle, so a few billions of years ago. Anyway, but now we have these rather sedate, beautiful clockwork orbits. So some simplifications we might want to make. So we've got Kepler's law here. I'm applying this for the solar system. So the mass is now m Sun. The little circle with a dot in it, that's the Sun. And the little m, that's the mass of the planet. And in pretty much every situation, you can see from the numbers here that really, basically I can ignore the mass of the planet. There's only a few systems, for example, Pluto and its moon, Charon. Well, actually, the masses are comparable. But for most systems, we can ignore the mass of the moon in these kind of calculations. So if you simplify that, we've got 4 pi squared over g m Sun, a cubed. Now, for the Earth, we know that p is a year, all right? And a is an astronomical unit. So this is a nice way of kind of recasting our formulae in units that are useful. And I certainly know from sort of my own experience and my students, sometimes that can be a bit of a leap of the imagination. Hang on a minute, how do we go from a formula here to this? Where have all the constants gone? So here's my sort of suggestion of how you can sort that out. Well, literally, think about this and its special case here. It's just the versions of the same formula. So if we literally divide this one, the general formula for our solar system, by this one, the sort of special formula for Earth, the 4 pi squared over g disappears. And in fact, the m Sun disappears, leaving us with p in years is approximately a in astronomical units to the power 1.5. So suddenly we've got a really easy calculation, which we can test very simply in a spreadsheet, that the period in years is the radius of the orbit in astronomical units to the power of 1.5. And that's Kepler 3 in its simplest form for our solar system. And you can almost do that in your head, almost. So there we go. So here we are. Here's a sort of the scale of the planets are clearly not accurate. There'll be dots on this system. Excuse me. Right. So yes, radio not to scale. So there we are. So p in years is the semi-major radius to the power of 1.5, and they'll all fit on this lovely curve. So can we try this? So I've got a Q&A popping up here. Once you know the angle from the tan function from the gradient, from the equation of the line. Yeah, all sorts of options here. As I say, I'm not probably going to get involved with how to predict those dynamics today. I'd recommend having a read. What I normally do with my students, I'm sure you'll do at school, is you'll start off with circular orbits, apply circular motion to work out what's going on with Newton's law of gravity. And then you might try mutually circular orbits. And then it's quite a big leap going up to the proper full Kepler problem. But it can be done, and it's something that I think all good sixth formers should get your teeth into before you go to study physics at university. So if you're lower sixth or earlier and you've not met this before, I would start with the simple ones, build your confidence up. But if you're knocking on the door of university and you want a challenge, see if you can solve a full Kepler problem. Look at my collectron notes if you need some help. There's lots of ways of approaching this, but it's a nice calculus fest. Well, we're going to look at this computationally. So I hope that's acceptable. Right. So we're going to have a quick look at Excel. This is possibly the best correlation I know. R squared is 1 to lots of significant figures. So let's go and have a look. So let's go and find one of our spreadsheets. So this is where it is. So if you've unzipped the zip file for today, solar system Kepler 3 is probably what you want. And I'm not going to do this one, from scratch. This is one of the spreadsheets. So what you've got is you've got the planets here with the semi-major axis in astronomical units, that's column B, and the period in years, that's this one. So what have I done here? Well, I've done the logs of both sides of this. All right, so if I do the log of this one, so if I do log both sides, basically I should get the log of this one is 3/2 times the log of this one. So if I have a graph which is plotting y, which is the log of my period, and x is the log of the semi-major axis, the gradient of that graph should be 1.5. So if you hopefully recognize the line of best fit spreadsheets, if you came to session 3, so I've literally used the same one, which it's all there. So if you want to do some line of best fit analysis, use the same technology, or even better, code it yourself in Python or MATLAB or another language of your choice. So look at that. We've got an R squared of 0.999. The error in the gradient is 0.019. It's tiny. So this is a really, really good fit. And in fact, I think I might have an even better value. That's a bug in the old versions of Excel. So this is pretty good. And what I've done is I've used my model curve. So if I look in this column here, that's literally the A value, which I've gone from 0 to where have I gone up to? Well, quite a long way. So I'm assuming that I could have planets, all ranges, and literally all this is the cell here to the power of 3/2. So as before, I can underlay my data with a model, a nice smooth curve, and you can see that that's pretty much every point, which is one of the planets. So I'm plotting. So these ones here. I select the data, data edit. It's B and C. So B and C are these data points here. So I'm underlaying my model curve, these ones using Kepler's law, that the period is semi-major axis to the power 1.5 in the right units of years AU. And I've underlaid our data with that curve, and we get a very satisfying result. But obviously to check that works and that correlates, we need a straight line graph. So we've done a log graph in our case, where we expect the gradient to be 1.5, and we show that's true to a pretty high degree of correlation. So there we go. That's applying our tools in the solar system. I think this is also a question in the homework, if you've been having a go at that. So let's just have a go at finding that. I think it's probably on a previous session. So there we go. Maybe look at the session 1 perhaps. And I think I've set a Kepler problem here. I was going to make that a bit bigger. There are the notes. There's the line of best fit stuff. And here we go. Yeah, so question 2 is basically what we've just done. So this is all the data for all the planets, including Pluto, and you're working out, this relationship here. All right, so if you want to give that a go, that's all the data. Interestingly, there's something called Bode's law. Now, does it bode well? Ha! So sorry about that. An interesting Bode's law seems to have to involve integers. So 4 plus 3 times 2 to the n is approximately 10 lots of the semi-major axis. So this is all kind of numerology. There might be some semi-good reason for this. But what you find is that if I go back to the spreadsheet, if you take that law, that's the blank one. I got the original. Let's have a look. Oops, I've deleted it. Right, let's go and find it again. So, error session planets. There we go. So if we apply Bode's law, so for Earth it's 1, N is nearly 2 for Mars, Jupiter's 4, Saturn's 5, Uranus is 6, Neptune kind of breaks the pattern, then there's Pluto at 7. So the question is, what happened to 3? So 3 is pretty much where the asteroid belt is. So there we are. Interesting stuff. Okay, so let's go back to our presentation. Any talks on the Q&A? Nope. Okay, fantastic. Right, so let's have a look. So if we've done our analysis in Excel for our solar system, well, what about other solar systems? Does it still work? Is this a universal law? Well, we keep telling you that physics laws are universal. I'm hoping one should never be cynical in life. That's something that might happen when you gain a few more years, but you want to try and avoid it. And there's always amazing things to find with physics and science. But we should always try and be skeptical. We should go, how do we know this is true? Proof by intimidation is not a valid form of proof. So we should say, how do we know that these laws are universal? Just because they're beautiful in their theoretical exposition doesn't mean we should believe that. So looking at exoplanets and Kepler-3 is a nice way of showing the universality of these laws. I downloaded this quite a few years ago now. As I said, they're probably at least an order of magnitude more exoplanets. This is a very nice website. I have to say, I hope I'm not impugning NASA or any of these amazing institutions by this, but I find it's quite difficult to actually get easy to use astronomical data from European Space Agency and NASA. I think sometimes what you find that smaller sort of enthusiasts often take the data and then put it into a spreadsheet that you can use. So this is a particularly good one, exoplanet.eu, and literally you can download a spreadsheet, which I've sort of simplified a little bit for, when I did it, 660 exoplanets. So what does it mean? Well, what we can look at. Indeed, yes, Cole Popper. So the little I think I've set up an argument here. So this is all about what we can prove in science. So maths is really the only discipline where we can prove things. In science, we can only infer. All right, we can show things are not true. We can show that I know the law of conservation of energy. That can be violated. In some situations, but we can show something. So if we had a perpetual motion machine, that cannot be true. But we can't actually ever prove things are absolutely true. We can show a strong correlation, because ultimately we have to start from axioms, but nature arbitrates whether things are correct or not. So we can only infer what nature is doing partially. So anyway, let's go back to philosophy, back to experimental work. So these are all our stars. There's the exoplanet, and there's our star here. So the way a lot of these are numbers, if you take 4UMA, 4UMAB will be a planet in that star system. So it's not like our systems where they have nice names. They have a little letter which denotes the planet. So we've got things like the solar mass, the exoplanet mass. Now watch out, it's in masses of Jupiter size. And then there are some upper and lower bounds to this. Sometimes these aren't symmetric either. So from an error analysis perspective, this provides a bit of a challenge for plotting your error bars. Blanched faces now. This is why kind of doing it in programming form, it makes life a little easier actually. We've got the orbital period. and again, upper and lower bounds. And we've got then the semi-major axis, upper and lower bounds. So let's just recap. We've got three things. We've got, well, four. We've got the star mass, the planet mass, the orbital period, and the semi-major axis. So we're assuming we've got these elliptical orbits. Right. So let's have a look at how we're getting on with this. So, all right, looks like a bit of maths. Let's just deconstruct this. So here's our Kepler's third law. Now, we need to be a little bit careful about this. So that's what is for a year. Okay. So this is our Kepler's law for the Earth going around the sun. So if we divide the general formula by that, we get what we had before, but now this factor in front. Now, why must we have this factor in front? Well, because the mass of our star is probably not going to be the mass of our sun. All right, our sun's kind of in the middle. It's kind of an average star in the main sequence. That's not going to be an average. There are some much bigger stars and much smaller ones in terms of mass. If we want to be really, really precise, we can include the mass of the exoplanet as well. Now, Jupiter was about 300 solar masses. The sun's 300,000 solar masses. So if Jupiter's a kind of typical exoplanet size, that itself is going to be fairly negligible. So actually, we can make our life easier and not have that bit. So you can cross that out. So there we go. That's usually the case in most situations. So what we're going to expect is a slightly different prediction. So if we do logs of both sides, 2 log p in years. Remember, it doesn't matter what base we use for logs because we're logging both sides. And we get the minus for this lot, and we've got 3 log this lot here. So if we plot, just having to think, yeah. So if we plot y is that plus this lot, okay, versus x, we should have a gradient of 3. All right, so not 1.5, but 3 in this case. And the difference is we've got this factor, which is going to be not insignificant. Well, we can get rid of that bit, but the log of the ratio of the log of our star mass and solar masses is going to be quite significant, possibly compared to this one as well. So we must have that involved. So does it work? Well, let's see. Let's find out, shall we? So here we are. Too small to see text, but I've done this in Excel, and it's a bit of an epic, but you can figure out how to put error bars in Excel. I'm afraid I'm not going to show you that today because it is a little bit fiddly, but I can show you a link. So if we go onto the Eclecticon, now where did I put it? All right, bear with me. Right, here we are. I seem to have got rid of it. Let's have a look. So if we go onto the Eclecticon, oh, there we are, it's up again. And under programming, I've got this sort of programming course, and there's something called Excel in Physics, which has all sorts of things in it. And you might find bits of the courses you've seen before. And in that, there's a how-to of how to do error bars, plotting error bars, this one here. There should be a YouTube video of how to do that. I'm probably sure if you Google it onto YouTube, you'll get lots of others, but that kind of walks you through how to do it. Worth a skill worth learning, definitely. Although really, you'll find it's quite tedious, and then you want to use a programming language to sort that out. Okay, so in some sense, having a go will force you to learn to program, which is a good result. Anyway, it's given me a Y value using my line of best fit calculator about 2.992 plus or minus 0.004. So it's not far off 3. It's good enough. What's the A in the formula again? Sure. So A is the semi-major axis. Let's call it the orbital radius. Okay. So again, a picture would be nice here to have to show up. So T is the orbital period, or P sometimes. A is the radius, the orbital radius. Okay, so there we go. Here's a sort of close up of this. So we've got a really strong correlation for all our exoplanets to Kepler's law. Slight difference to what we've had before our solar system, because we've got this extra factor here, noting the masses of our stars are going to be different. All right, so we can't just use the same formula. The M is going to be different. All right. Okay, so here we go. That's how I did the line of best fit using the software we had before. Again, the text is a bit small, but you can sort of see how I've done it. I don't know if I can show you the spreadsheets where they are. So here we go. So I think it's 2019 Excel analysis, and all the bits are there. So I think that's one of them. If I just load this up, which one's this? Yeah, there we go. So that's the Excel file if you want to give it a go. Again, it's quite a busy one because you've got to work out all the errors in X and Y. And that's what will take, 60% of your time to figure that out. But it is worth doing as an exercise. And notice you've got your graph, you've got your maths. We probably ought to have a nice picture of an orbit as well to define our numbers. But there we go. It's all there if you want to have a play with it. And the line of best fit version, I think it should be this one here. Yeah, there we are. Okay, so all these are real spreadsheets. I've not just made them up. Okay, so unless there's any other open questions, let's carry on. So hopefully you can think, well, that's all very good. We've shown, not proven Kepler's law, but we've shown that Kepler's third law correlates very, very strongly to solar systems beyond our own, which is a pretty good thumbs up for science, I think. But we've also probably thought, hang on a minute, looks like a bit of a hard work to do that in Excel. We're getting quite a lot of data now. So is there a better way of doing this? Well, yes, there is. So we're going to look at how to do the analysis in MATLAB. So particularly the error bars. So here we go. So this is the output, and you can really produce some fantastic plots using programming languages. For science, this is really the goal, is how you can make figures which really communicate the information you want. So the blue dots are the model, the red dots are the data, and the green lines are the error bars. And some of these error bars are massive for large orbits and large periods. Okay. Interestingly, there seems to be quite a lot of data which is closer in than the Earth, so quite close to their star. Okay, so and one that it's not so easy to do in Excel is basically what I've done is I've plotted well, one versus the other. So this is my prediction. So this is my orbital period, t squared, and this is what I think it's going to be. So a cubed over my mass radius. So essentially what I'm doing here is I'm plotting my measurement versus my prediction, essentially. And we expect in that case a one-to-one relationship, a y equals x graph. So, as an analysis tool, unless you're trying to figure out something from the gradient, like strength of gravity or whatever, then actually plotting measurement versus model is the first thing you want to try and see how close that is to y equals x. In this case, we've got a very strong correlation. 0.9455 for all our data. So it's actually probably a bit clearer to see the correlation here than it is for that. Okay. Anyway, so how might we do this in MATLAB? Well, just very briefly, I'll show you the code itself. So if we open up, so if you want to give this a go, 2018 MATLAB analysis, and I've got something called Exoplanets. So what it does is it loads up an Excel file here. That's the sort of raw data, and then produces all the graphs. So if we open that up in MATLAB, and what I'll do, I'll just sort of skip through the basic bits of it. So here we go. If I move it over there, we might get the graph to show. So again, the green is commentary. So always when you're coding, particularly if you've never coded before, start telling yourself what this thing is going to do. So that's my Kepler's third law, and it just exploits the relation. Okay, so it hasn't, it's not really a recipe as much. And then I'm going to write my recipe out. The function bit means everything happens within this little sort of sandbox. And I only expose parameters outside of this if I deliberately want to. So I've got some sort of inputs here. It's always good to have your inputs at the start. And then I'm going to sort of, I'll put a breakpoint here and see what goes on. So if I run this, I skip to the next stage, he says. Here we are. So now I've got arrays. So if I look at the array num, it's now appeared here on my screen. Basically, that's the spreadsheet I've just ingested with just the numbers to it. If I look at raw, that's the actual spreadsheet itself with all the names and things. So num is that strips out any text. So essentially what we've now got is a spreadsheet inside MATLAB. And what I'm going to do is I'm going to take off all little columns and call them things. So if I step through this, M is now an array of all the masses, a sort of 660 by 1 vector. Then I've got the planet masses, and the plus or minus bits. So there we are. So that's the planet masses, the orbital periods, etc. So what's nice here is that I'm taking every column of my spreadsheet and I'm calling it a variable. And then I can use those algebraically. But remember, they're vectors. Each one is 660 rows in one column, because MATLAB stands for Matrix Laboratory. So that's what you're dealing with. Anyway, so I then form the things that I'm predicted to be true. So there's my Kepler's law. All right, so I've got these things sorted in ascending order, and then work out the sort of the plus or minuses. So I'm going to need that to plot my error bars. I've got some limits. Some of my errors are huge, so to avoid problems in my plotting, I'm just going to get rid of them. That sounds like dodgy science, but it's just literally, I'm zooming in on my data set essentially. I then find my line of best fit. So that's the best fit function. So let's get through this one. So if I scroll to the bottom here, after my plot routines, I've got some functions which do things. So this one is a line of best fit of a y equals mx plus c kind of idea, or y equals mx kind of idea. So this is in code the recipe that we talked about in week 3. And that's nice, is that when you're coding up, anything that's an operation you want to repeat, like find me the line of best fit, you can write as a subroutine, a function, which you can call as many times as you like. And a nice sort of programming paradigm is to basically function up your stuff. So rather than having lots of repeated operations that you could accidentally code wrong, have them individual functions. So all you need to do is test it once, and then if you make a change here, it will change all the other things as well. So once we've worked out the model and the line of best fit, then all we have to do is plot it. And these are the error bars. So I'm literally walking through a for loop of all the different things. Let's just do it a couple of times. So here's my figure, there's my data, model versus measurement, and then we'll plot some error bars. You can see I'm going to go through all of these. I think some of these are too small to see at the moment. Oh. Yeah, you can just see a couple of error bars here. So let's skip to this one. F5. There we are. Now we've all got our error bars. And then it's just a case of adding all the annotation to our graph, the limits, the legend, the X labels, etc. All right. And the difference between the purple text and the other things is that this bit here, for example, in the title, this is how I mix a number to string. So in this case, the length of number of my exoplanets. So how many exoplanets do I have? I turn that into a string. I concatenate that with my text, exoplanets T versus A. In Python, that's even nicer. You just use a plus. And the last bit is we make a picture of it. So there we are. If I just step through that process. There we are. That's all done now. And there we go. All sorted. Pre-made libraries for easier MATLAB coding. Well, yes, you can download my code. So all you go. I mean, in terms of plotting graphs, every graph is going to be distinct. The commands are all the same, but the titles are going to be specific to you. So you can't. There's not really a library for that. But the best thing I suggest is that download my code, adapt it to your purpose, and hack it around. It's nice to start from scratch when you know what you're doing, but why not reuse something? That's how all programmers do it. They write something and then they reuse what they've done and repurpose it for something else. So this code here is essentially, what have I done? I've loaded a spreadsheet. All right, I've extracted some data from that. I've sort of worked out the error bars, the sort of plus and minuses, that kind of thing. I've ignored a bit of data. I've applied a line of best fit to my subfunction, and I've plotted loads of stuff. And that's quite a generic process. We could adapt that to almost anything. Okay, so I think you just got to get stuck in. There's lots of courses for sort of basic MATLAB, and there's lots of good books. I've got it very close to my desk. Yes. So this is something I recommend. You can see it's on the camera. Mastering MATLAB. It's a lot later than MATLAB 6 now, by Dwayne Hantsman and Bruce Littlefield. It's not too fat. Very, very good book. That's quite nice to have next to you. There's lots of stuff you can go online. There's the MATLAB file exchange, but as I say, if you for this course, we've got loads and loads of MATLAB things to get stuck in, and you can easily copy it into Python and change the syntax. So there we are. So that's sort of how we created those graphs. So we have time. All right. Okay. So let's go back to our little presentation, and let's have a look. So obtaining exoplanet parameters. So we've got all this data. How do we find it? Now, there's an interesting question. So a bit of text here. So in January 2021, 4,395 confirmed exoplanets in 3,242 systems. So with lots of these having more than one planet. So this is almost, this is an order of magnitude pretty much more than when I did it a few years before. And it's going to probably expand exponentially. So how do we detect exoplanets? Well, there's a whole bunch of things. So the most popular one is to look at the dip in luminosity. So the star radiates, and your planet basically goes between you and the planet. It's like a partial eclipse. And you'll see some of the planet's lights, the star's light blocked by the presence of your exoplanet. So you don't detect the exoplanet directly, but you detect the luminosity, the power unit area, well, the power from the totally radiated from your star, and that will dip, and from that you can work out the dynamics of your planet. We can also look at the Doppler shift, so the spectra from the star, how that changes due to the motion. Now this is really cool because this is about the motion of the star about the center of mass of the star planet system. And this is going to be involving a very tiny movement, very literally a few meters per second. It's amazing we can actually detect this, but we can. Nowadays, I think there are some direct ways of doing this, literally by looking at it. You can actually see the exoplanets. Although if you think about it, exoplanets aren't very bright usually, so that's going to be quite difficult. And there are many more exotic techniques, such as gravitational microlensing. So this is where the gravity itself, the sort of gravitational fields, will act as sort of, well, the planets will act as lenses. So electromagnetic waves will be affected by gravity, sort of Einstein's equations, and you'll see sort of high mass systems act like lenses. So you'll sort of look at the distortions and you can work out the mass of the thing that's caused the lensing effect. Anyway, lots and lots of other things. There's a Wikipedia page with a few of them. So let's look at the luminosity method. So here's the transit of the sun by Venus. All right, don't look at the sun directly, but with a sort of appropriate filter, you might see something like this. You can see all the solar coronae or coronas, and you can see the sort of black dot as Venus comes past. This is a sort of time lapse. Amazing stuff. So what do we find? Well, we can work out the fractional luminosity dip. So flux is going to be, well, sort of photons per second, or it'd probably be something like power per square meter, something like that. And the dip is, if you think about it, will be the fraction of the area that's obscured. So if it's within your solar disk, the pi r squared for Venus divided by pi r squared for the star is going to be your dip in luminosity, because the luminosity will be proportional to the sort of surface areas. The power radiated is proportional to surface areas of your star. So there we are. We should expect that ratio to be this one here. So if we know the ratio of our star, we can work out, and we know the dip, we can work out R. So there we are. So here's the sort of formula of this. So here we go. Here's our planets. Sorry, here's our star, and here's our planet. I'm assuming we've got a system where the masses aren't that different. So in a binary system, they would orbit about their common center of mass. We call it the barycenter. For our star, for the sun, that's going to be pretty much the center of the sun. But the barycenter for, say, Pluto and Charon will be outside of Pluto and Charon. All right. Good calculation to do that one with the Earth-Moon system. I think it's within the Earth. So here we are. So luminosity versus time. You'll actually have a very tiny dip. And if you think about it, we can work out that time is actually, so big R here is the radius of that, that sort of how it crosses the surface of the sun. Divide that by the velocity, and we've got the time it takes. So if we know what the orbital speed is, we can work out a few of those things as well. So b is going to be the distance from the barycenter to the planet itself. So from that, we can kind of relate those variables. So from that, we can basically work out a formula for the radius of our planet. Okay, so this is our dip. All right, so we've got the dip in luminosity. So the luminosity, the change in luminosity is the ratio of the radius of the planet to the star squared, because it's the areas. So if you rearrange that equation, we've got the square root of the fractional dip in luminosity to the luminosity of the star when there's no eclipse, multiplied by the ratio of our star. Well, I've divided everything by the radius of the sun, just to make it sort of easier. So this is in the radius of our planet in solar radii. Okay, we could do it in Earth radii if you wish. So there we are. If it's an Earth radii, we need to multiply it by the radius of the sun divided by the radius of the Earth in kilometers. So there we go. So if we know the luminosity dip, we know the luminosity of the star, we know the radius of the star, we can work out the radius of the planet from that calculation, which is pretty good. So apparently this is a real image. This is the moon. So this is taken from the Deep Space Climate Observatory. It's got a kind of good disc of someone that's been a long time working on that acronym. And that's actually the moon coming between the satellites and the Earth. So there we are. So another way of doing this is to use radial velocity. Okay, and this will give you the mass rather than the radius. So this is the radial velocity of my my planet as it goes. And notice it has this sort of oscillation to it, all right, because it's circular motion. It may not look like circular motion, but if you think about it, it's the radial, it's the projection of my circular motion. So if I'm going around in a circle like this, you know, my radial motion will be going in a sinusoid, which is what we can see. Now, so firstly, what's a Doppler shift, you may ask? Well, this is my favorite model for Doppler shift. This is another nice thing to program up. So what we imagine you've got a kind of, you know, like a sort of, imagine you've got a tame duck that's flying over a pond. And this duck is dropping, you know, it's got some food in its mouth, got a load of stones or some seeds. And every sort of second, the duck drops a seed into the pond, all right? Maybe a stone might be a better analogy, it will sink a bit more. So every time, so the duck drops its first stone here, second stone there, third stone there, etc. And currently the duck is here, the red star is. So at that point, the ripple from the first stone is the dark blue color. All right, so it's radiated out from that point. That's the center of the dark blue circle. When it sort of the second stone has got to this one, but of course its center is a bit further along to the left because the duck was moving before it, you know, dropped the stone. And so what you can see is that the ripples bunch up this way, and the ripples are getting further apart on this side. So how do we interpret that? Well, if a source of ripples is coming towards us, then our wavelength is going to be blue shifted. What does that mean? It means the wavelength is reduced. All right, the frequency has gone up. It's Doppler shifted. And if it's going away from us, we experience the you know, each subsequent source of wave is further away, so the wavefront you know, is a bit further apart. So it's red shifted. The wavelength has gone up. The frequency's gone down. So there we are. That's a visual demonstration of the Doppler shift. You can do this with a compass and a ruler. It's a nice thing if you've got a few hours to spare and a big piece of paper. That's a nice exercise. But you can code this up too. This is obviously what happens if the source speed is slower than the wave speed. If it's not, you get a Mark cone, which is a shock wave. All right. So now this is pretty cool. So remember, if we're going around a circle here, we're getting that. This is all about luminosity. So we'll talk about the main sequence in a moment. So this is something that's really, really amazing, is how we can work out the masses from these Doppler shifts, because the shifts are really small. So if we had a star going around this orbit here, and the planet in a mutually circular orbit, this is their center of mass, we can work out the Doppler shift based on the projection of the radial velocity on our direction. So u cos theta is giving me the projection in, that's where our eye is looking. So u cos theta over c is approximately the Doppler, the fractional shift in wavelength. I haven't proven that, but it's not too difficult to prove that from that kind of construction here. Again, have a look on the eclecticon if you want to see proof that, or just Wikipedia it. Anyway, so we're trying to measure this orbital speed. Now, how do we get the wavelength? Well, there's a relationship between the temperature of your star and the wavelength, because these all stars, well, anything that radiates will follow this, what we call the Planck emission spectrum. This is wavelength versus irradiance, which is sort of watts per square meter per wavelength. And the hotter you are, the shorter the wavelength of the peak is, and the larger the area under this graph. The area under this graph is actually constant times the temperature to the power of 4. This is called Stefan Boltzmann law. Now, so we can measure the spectral intensity for our stars. We can use a spectrometer to sort of see what this looks like. And if we work out the maximum wavelength, so the wavelength at the max of the peak here, that is actually related to the temperature of the star. It's called Wien's law. So it's a constant divided by the temperature in Kelvin is equal to the wavelength associated with the maximum in the spectrum. So this is all relies on having a really accurate spectrum of the light from our star. Now, what you can find, if you work that out with exquisite precision, and we can see how exquisite that has to be, all right, then we can actually see that maximum that wavelength at the maximum at the peak here actually varies with a certain period. So we can use that to work out what the Doppler shift is going to be. And the maximum of this over the, so that change over this maximum is the ratio of those speeds. But that's not the speed of oh no, this is the speed of light. Okay, so okay, a bit of math more to go. So we probably want to do this in slow time. But from Kepler 3, you can work out the semi-major axis for this system based on the masses, if we know those. So that's the mass of the star. All right, let's just say we work those out. There's the period of our orbit. We can apply Newton's second law now for, but we've got to be a bit careful about this. This is for the actual star, the circular orbit of the star, not the planet. All right, so this is going to be a really small orbit if you've got a very massive star system. And if we can do that, we can actually find the mass of our planet. So the mass of our planet is going to be the square of the orbital speed of my star multiplied by the square of this distance here, the orbital radius of my planet. So finding out u is the tricky bit. So a bit more rearrangement. If we put all this together, we can actually work out the mass of our exoplanet. So what do we need to figure out? We need to find its orbital radius, which we can get from just looking at the time between eclipses. We can get the orbital speed from our Doppler shift, and the period. Well, that's quite easy to find. So the tricky thing is to find u, the orbital speed of our star about the center of our barycenter. Now that's not easy, but it is possible for looking at this tiny variation in our, from our Doppler shift. So there's other ways of doing it as well. These are direct images apparently, and this is gravitational micro lensing. So what you find is that have we got a good picture here? Here we are. So here's your observer. Here's your light source, and you'll see that the light tends to be sort of bent by the presence of the sort of gravity of your planet here. Very, very tiny effect. Here we are. So this is a sort of classic images of a gravitational lens. This is actually a galaxy behind, which has been sort of distorted by a more distant blue galaxy. So there we are. That's so the red galaxies in the foreground, and the galaxy behind it. You'd not normally see it, but it's sort of made into this ring. From this distortion, you can work out sort of properties of the masses of those things. Now, before we leave, how do we work out the temperature of our stars? How do we work out the mass of our stars? We've already shown that if we know those things, we can work out the mass of our planet from these Doppler shift. But how do we know the mass of our star in the first instance? Well, we can make some sensible guesses. And there's something called a Hertzsprung-Russell diagram for the main sequence of stars. And so what are correlations do we know? Well, we know from Wien's law that if we can measure the wavelength, the peak of our spectrum, right, this one here, we can work out its temperature from Wien's law. So if we know, so we measure this, we can do that quite relatively easily. We can find out the temperature of our star. So that's in solar temperatures. All right, so that's about 5,000 odd degrees. And that's the lambda max for our sun, 502 nanometers, so in yellowish. Now, how do we find the mass, the radius, and the luminosity of stars? Where do these powers come from? These are correlations based on the main sequence. So let's have a look at this. So this is our Hertzsprung-Russell diagram for stars. So we've got surface temperature, luminosity, and there appears to be some correlations. It's not quite a straight line. And there's like a branch here for giants and supergiants and red dwarfs, etc. But in the main sequence, at least, there are some correlations. So this is where you can stick things into a spreadsheet and work things out. So here we go. Here's some stars I got from Wikipedia, all sorts of different ones, from brown dwarfs to our sun to a whole range, all in the main sequence. And so I plotted the log of luminosity versus the log of temperature, and the log of mass versus the log of temperature for each of these. And lo and behold, you get pretty good correlations. So if we know temperature from wavelength, we can find mass and we can find luminosity. And that's indeed what we do. So putting this all together, we can make ourselves a spreadsheet. And so I've done this for Kepler 452b and its star, which is Earth 2.0 apparently. And you can work out things like, the orbital radius. This is the input data. And then these things here, we can work out from our correlations, all the other bits. So you can basically work out a kind of top trumps card for your system based on those parameters. You can download this spreadsheet from our directory, which is Exoplanet Analysis. I think it's this one. Yeah, so there we go. That's the spreadsheet there. So it's all the code. And you can have a play with that. Find a new exoplanet, stick in the numbers, see what happens. And there's a little note here which has all the maths behind it, if you want to have a look at that too. So that's Earth 2.0. Let's have some of the numbers of here. So the star surface temperature is about 2% higher than our sun. Let's have a look. What's the planet itself? So the orbital radius is very similar to Earth. The planet mass, actually it's a 5 times the Earth's mass. It is quite different, as you can see here. The radius is 1.5 Earth radii, so it's a bit bigger than Earth. But look at this. Look how small the Doppler shift is. So the Doppler shift is about 7.23 times 10 to the minus 7 nanometers. Absolutely tiny. So it means the planet itself is going at about 0.43 meters per second. So this is the star. The orbital speed of the star at the barycenter is about 0.5 meter per second. So think about how difficult it is to detect that. So that's a real triumph, but it can be done. This is 700D, which is more similar to Earth. Maybe there's liquid water on it. We don't really know. So that's an artist's impression. That's 1.72 Earth masses. So the radius is only 20% higher. The orbital period is 37.43 days, though. So seasons are going to be quite different. There we are, and it's much closer to the sun. So do we know what the luminosity is? Yes. So the luminosity for this is very small. So this is going to be a kind of brown dwarf, a really old star. So this is much closer to the star. So we might have a very different situation than our sun. We're much closer to the star, so therefore we might be receiving similar heat. And there we go. So I hope that's been fun. A sort of tour of Kepler's laws, exoplanets, how we might go about finding these parameters. And that's really the interesting story here. How do we know this stuff? How can we calculate it? And I think that the key take-home point here is that the Doppler measurements for finding out the speed of your planet, your star, around its barycenter, that has to be discovered to really exquisite precision. But we can do that with spectroscopy. So hopefully some of you may start to go into astrophysics. Maybe you can come and write to me with some discoveries of your own. Anyway, thank you very much. Unless there's any, how do we detect such small wavelength shifts? Well, what you do is you observe the light for a long time, and you will do something called a Fourier transform, which takes the signal of that light and basically says, well, how much of that light is in certain frequency bins? So, and the more you stare at your star, it's a bit like if you want to listen to some music. You listen to some music for a few seconds at 44,000 samples a second. You can then work out the spectrum of that, so what frequency content is in that signal. And the longer you listen for, the greater the resolution in frequency you can detect. Okay, law, theory, model. Right. Okay, so again, this is a bit more philosophical. So a law of physics, like Kepler's third law, right? Relating, we've got a model of something whizzing around a circle, and so we can maybe sort of make a little animation to sort of show you that. Let's go for gravity sim. Let's have a look. Circular and elliptical orbits. Do I have? Oh, here we are. There we are. So here's Kepler's law. So something going around an elliptical orbit around the sun. All right, that's a model. Okay. So the law is how the parameters of this model interact with each other. It's the maths, basically. And a theory is the sort of, well, Newton's laws is a body of physics. So they are kind of semantically the same kind of thing. But I like to think of a model as a sort of a dynamic mathematical system which we can make simulations from. So if we've got a simulation here, let's go for, well, this might be a good one to end. So this is going to be in a few sessions, I think 2 sessions time. We'll have a look at this. So we've got, let's look at this one. Here we are. So we've got, let's go 3D. There we are. So this is going to be 2 suns in a mutually circular orbit. And I've got little planetlets. Let's just restart that so you can see what's going on. So there we are. So you can see these sort of circular rings around each one. And so each of these rings feels the gravitational wind from both of these stars. And you end up forming these amazing sort of tidal tails, which is something in which we see in galaxies. So all of this stuff comes around spontaneously applying Newton's law of gravity, and that's about it. Okay. Right, well, thank you very much. I'm a few minutes over, so unless there's any more questions, then I will sign off. So thank you very much, everybody. Oh, it's worth saying, remember, there's a break next week. We're on half term, so I'll see you in 2 weeks' time.